Hi, I'm Gary Rubenstein, and this is the 11th part of a series of videos I started making that goes through my thoughts on elementary school, middle school, and high school math. Started with kindergarten math, and I've been working my way up. I'm currently in what's in like 8th or ninth grade, making a couple of videos about algebra. And up until now, our algebra equations have been things like, x plus 2 equals 10. And we learned that you can do stuff to both sides, maintaining the balance of the equation, until you get an equation that's so obvious that 8's the number that makes it true in this case, and 8 is also the number that makes that original equation true. But today's video is about what are called systems of linear equations. Systems of linear equations is where there's two variables. So imagine instead of saying x plus 2 equals 10, I say x plus y equals 10. So that question, if you think about it, that doesn't have an answer. It has many answers. There's many things that add up to 10. 9 plus 1 equals 10. 8 plus 2 equals 10. You could even swap it around and say 2 plus 8 equals 10. You could even throw in some fractions. And there are an infinite number of ways that we could fill in for x and y. But it's not just like any two numbers. Like, there's plenty of numbers that don't add up to 10. 5 plus 6 doesn't add up to 10. So when we say infinite answers, it does not mean that it's not the same thing as saying every single pair of numbers makes it true. When more than, for this equality that said x plus 2 equals 10, we can call the solution set. We use these curly braces. And we put in all the answers that make this original equation true. And all of them ends up just being one thing. But for this x plus y equals 10, the set of solutions, the way we do it is we write in a little parentheses, see 9 plus 1, so x equals 9, y equals 1 is a pair that makes this true. And what we often do is we write those two numbers with parentheses around them, with the one that goes for x first, the one that goes for y second. That's called an ordered pair. It's an ordered pair because it's not exactly the same thing as 9 as 1 comma 9, which also works in this case. But I could have a more complicated equation like 2x plus y equals 10. And that might have 4, 2 as one of its solutions, but y equals 4, x equals 2, does not make it work. Anyway, this solution set would actually go on forever. I could use negative numbers, fractions, all kinds of things. So this thing doesn't have a single satisfying answer. But if I add a little more information, here this giant parentheses thing, brackets, is not actually the same as this one, which is for sets. This is what we use for what's called system of equations. This is where I tell you that x plus y equals 10. But I'm going to give you an extra piece of information. I'm also going to tell you that x minus y is equal to 4. Now, x minus y equals 4 has a lot of things that make it true. And x plus y equals 10 has a whole bunch of things that make it true. But there's only one pair, in this case, that makes both equations true simultaneously. and you can mess around with them. I think you'll pretty quickly come up with 7 plus 3 equals 10, and 7 minus 3 equals 4. So this thing, otherwise known as a system of equations, that's when you have two equations with two different variables. And this system of equations has a single solution, the ordered pair 7, 3. Now, there are, besides riddles that I could make up, find two numbers whose sum is 10 and whose difference is 4, systems of equations do actually come up in real life. I could make up a word problem that says something like, if X, let's say I'm selling tickets to the movies, and X is like the number of adults I sell to, and Y is the number of kids I sell to. And maybe I say, okay, well, the place holds 200 people, so they have to add up to 200, the total number of people. But the amount of money that I bring in, maybe I sell tickets for $10 to each adult and for $4 to each child, and I bring in, I'm just going to make up a number and say $510. See how this has like the same kind of feel as this one? There's an X and a Y, and there's so many things that make the first equation true, and there's so many things that make the second equation true, but generally there's one thing that makes both questions true, both equations true. Sometimes these are called simultaneous equations because we're solving them sort of at the same time. And I just want to say some stuff about this. We're hitting a realm right now where it really wouldn't matter if in life if you learned systems of equations, and that happens at a certain point in math where you really could survive in life no problem. There's a little geometry that's coming a couple of videos from now that's real important, but otherwise the rest of the videos are you could easily live without them, and people did live without these skills up until very recently. They really weren't even part of the math curriculum. I'm talking like in the 1700s where all this stuff was still known. They didn't think it was that necessary to teach it to people. And yes, sometimes these things happen, and if you're a computer programmer, you need to know this kind of math sometimes, or certainly in business, they sometimes have business models where you're going to want to know, like, what should I do? Here's my two things of production. I have to produce this many of this widget and this many of this other type, and I want to make it so I make this much money, but I want my expenses to be, this much. There are systems of equations that get used in life, but for practical purposes, most people, if they ever learned how to solve these sorts of equations, they would have forgotten it and never really hurt them in life very much. But I do want to show you them. It's a big part of math, and I find it to be kind of interesting. So I'm just going to show you a few things like to think about. Systems of equations. Imagine if I have something like this, 2x plus 5y. And I'm just going to put up here, I'll say 7x. And I'm going to make up some numbers and make this a nice answer. Hold on a second. Okay, and here I have my system of equations. You don't need to put this little curly brace, but you can. Now, just like before, each of these equations individually has infinite pairs of x's and y's that make them true, but there's only one pair that makes them both true. And imagine this was stuff that costs money. So I have things that cost $7 and things that cost, sorry, let me change that. 7 hamburgers and 5 hot dogs cost $41, and 2 hamburgers together with 5 hot dogs cost $26. So X is the number of hamburgers I'm buying, and Y is the number of hot dogs. And we want to know how much does each thing cost. Well, notice how, well, there's more hamburgers in the first case, but there's the same number of hot dogs in both cases. So the difference, if I subtract 41 minus 26, I get 15. That $15 difference, because the hot dogs had the same number, which that didn't have to happen, but I want to start with an example where these two numbers are the same. So that $15 difference can only come from here, from the change in the number of hamburgers bought. And 7 minus 2 is 5. So the difference, this $15 difference, came from the fact that there were 5 more hamburgers in the first case than in the second. So that $15 accounted for the 5 more hamburgers, and 15 divided by 5 is $3. That must be the price of one hamburger. That would account for the fact that the hot dogs being exactly the same, the difference in the change in price had to come from the fact that there were 5 more hamburgers, and 5 times 3 is 15. Well, now that I know how much one hamburger costs, I can take either of these equations. I can say 7 times 3 is $21, plus 5 times, I don't know how much a hot dog is. Then I can say 21 is 5y plus 5y equals 41, which means the 5y has to be the other $21, which means that y has to be 4. And that's the answer to this question. Had you instead looked at the bottom equation, you would have said, well, 2 times 3, that's 6, but it has to add up to 26 altogether. So that means that the other $20 has to come from the 5 hot dogs. And again, we get y equals $4. So I wanted to show you how you can kind of like reason out a question like this. But now I want to show you like more formally. So the question was 7x plus 5y and 2x plus 5y. And this was 41, and this was 26. So the trick is that if you have like the x's or the y's are the same, you can subtract the two equations. And you end up with 5y minus 5y is 0y, but 7x minus 2x is 5x. And we call this elimination, when one of the variables like disappears when I subtract the two equations. And then you divide both sides by 5, and you get x equals 3. And then you substitute that 3 into either of the original equations. And you get our answer, which is x equals 3, y equals 4. Well, this is great if those numbers match up so nicely like they do. But what if they don't? So what if instead my question was 7x plus 4y equals, and 2x plus, let's say, 6y equals. Here's some numbers for afterwards. So now we really have a problem. We can't use the same trick as before, because if this is hot dogs and hamburgers again, well, yes, it's $30. It's cheaper when you get less hamburgers, but you also get more hot dogs, and it's really hard to compensate for that. We really wish that it was like the first example, where it was the same number of hot dogs. Then the difference in price could be accounted for by the difference in the number of hamburgers, which would tell us how much each extra hamburger must cost. That didn't happen here. And this happens a lot in math. I wish these two numbers, the 6 and 4, were the same number. Well, good news. If 7 hamburgers and 4 hot dogs is $37, then I also know how much 14 hamburgers and 8 hot dogs would be. It would be 74, because everything's doubles. In other words, 14 happens to be twice as big as 7, and 8 is twice as big as 4. I don't know everything, but there's other things I know. Like if I multiply everything by 3, take that top equation again, and say 21x plus 12y, well, that would be 111. 3 times as big as 37. And I could just keep doing that. I can multiply everything by whatever number that I want. But is that useful? Well, I could also do that with this bottom equation. If I double everything there, twice as many hot dogs, twice as many hamburgers, it's twice as much money. So now I have all these 1, 2, 3, 4, all these equations. They're all true. But notice how this one has a 12 and this one has a 12 also. 12 is what's known as the least common multiple of 4 and 6. If you think of the 4 times tables, and you think of the 6 times tables, I don't know what that one's doing there. The number 12 appears on both lists. So the trick to this question is to take the original thing and multiply the first equation, everything on both sides, by the number 3 will turn this 4y into 12y. But for the other equation, multiply both sides by 2. So this equation turns into 21x plus 12y equals 111, and 4x plus 12y equals 60. So those are true things. But now take a look. Now I can do that trick from before when I subtract. See the difference now, $111 versus $60, $51 difference. But since they have the same number of hot dogs, that difference must have come from the difference in hamburgers. There were fewer of them in the second case. How many fewer? Well, 17. So 17x equals 51 divided by 17. X equals 3, just like before. Then you can plug that 3 into any of the equations you see on this slide, including the very original one. 2x plus 6y equals 30. Put 3 in for x. 6 plus 6y equals 30. That means that 6y has to be 24, and y equals 4, just like before. So that's how it works with systems of equations. And just to show you, there's famous riddles based on these. There are 50 animals. Some are two-legged animals, and some are four-legged animals. And I tell you there are 50 animals, and there are 100 legs altogether. So then we want to know how many of each animal are there. So you say, well, the number of animals is 50. But the two-legged animals, there are X of them, so 2X is the number of legs that altogether that those animals have. And then the 4y is the number, 4y is how many legs the four-legged animals have. So there's my system of equations. I wish these y's were the same number, and I can easily make them the same number by taking this first equation and multiplying both sides by 4. So 4x plus 4y equals 200. And that equation I can solve. See how the 200 is bigger than the 100, but the 4y is the same? So if I subtract, I like to write these with the thing I'm going to subtract sort of above it, although there's no rule that you have to do it that way. So you see, these two situations are true also, that 4x plus 4y is 200 and that 2x plus 4y is 100. Well, those both have 4y in them. So when I subtract, the difference in that number, the 200 versus the 100, comes from the extra four-legged animals. So if I subtract these two things now, I get 2x. These sort of cancel out, as we say. 200 minus 100 is 100. Oh, well, this... well, I made a bad question, because this ends up just being x is 50, y equals 0. So that wasn't a very... of course, I have 100 legs. I had intended the answer to be 38 and 12. Let's see what went wrong there. 38 times 2 is 76. Ah, yes. 12 times 4 is actually not, contrary to popular belief, 24, but is 48. So I should have said 124 legs. I like that question better. So x is actually 38 in this case. And then you can go all the way back to the very first, the 50 animal question. So if there's 50 animals, that means that the four-legged animals has to be 12. Once you know how to do systems of equations, you get to be inducted into the club of the famous cell phone plan question. This is the question that's supposed to make everybody feel that math is, so relevant. This question doesn't make math so relevant. I mean, I think math is relevant if it's thought-provoking and if you're liking it. And yes, it's used in science and business. The cell phone plan question goes something like this. One company charges, $10 a month plus $2 for every hour that you talk on the phone. And the other company, they charge $30 a month, but they only charge $1 for every hour you're on the phone. So depending on, like somebody who doesn't talk on the phone at all, say when x equals 1, cell phone plan 1 versus plan 2. Cell phone plan 1 costs $12 at the end of the month, whereas for plan 2, it's $31. So if you use the phone very little, you'd want to go with plan 1. But if x is really big, like you're on for 50 hours, then this first one becomes 110, whereas the second one only becomes 80. So for certain situations, the second plan is better depending on your needs. And then the question becomes, yes, plan 1 is better up to a point, but after that point, Plan B becomes better for you, and the question is, what's the break-even point where the plans cost the same amount of money? Something like that. If you subtract the two equations, because they both have y, you get 0. Hope you don't mind if I'm going to put the, let me just rearrange them. Zero equals 20. Still, 1x minus 2x is negative x. And you end up with x equals 20 is the break-even point. If you put 20 into either of these equations, you get, in the first one, you get 10 plus 2 times 20, which is 50. And for the other one, you also get 50. So in this case, you would know, well, if I'm talking on the phone for less than 50 hours, I would choose cell phone plan number 1. Whereas if I talk on the phone for more than 50 hours, I'd be better off with cell phone plan number 2. This question comes up in so many different forms over the years, but now it's basically a very famous question. Again, that question's not like that relevant, and most of the math from here on in, I hope if you're still with these videos, you're trying to learn like what are the little tricks that we can do in math and the types of equations that we can, and if I'm helping my kid, well, maybe you're better at that now also. Okay, I'll see you. If you've come this far, you're going to go all the way to part, is it going to be 25? Maybe.